This is an introduction to exercise 6.2 on stationary points. Again, as I mentioned, we're going to focus on turning points, stationary points, and generally how to identify them. It'll be a very brief video. We're just reviewing our previous understanding. So, of course, stationary points occur when the curve has a zero gradient at a point, obviously considered a stationary point, and as we mentioned, there are different types of stationary points. There are your turning points, your maximum, local maximum, your local minimum, and of course your stationary points of inflection. Just a quick reminder that not all points of inflection are stationary. If your stationary point looks like this, of course that is a stationary point of inflection. There is a gradient of zero at some stage. However, a point of inflection can look like this. In which case that is not a stationary point of inflection, and it is something that can come up on your calculator. We can determine each stationary point by examining values around the stationary point itself. So I'm assuming you've done sine graphs that look a bit like this before. Yeah, okay. You can do some variant of that. If not, you can do just a general graph or a table that indicates the gradient of values at each point. So let's put that into practice. Let's quickly look at example 16. Of course, because we know the gradient is represented by the derivative function, I'm going to first find the derivative. It's very straightforward. I'm just going to find dy dx. No fancy stuff here. That's just going to be 3 minus 3x squared. Because we're looking for stationary points, I need to then let that equal 0. So I'm going to write let 0 equal to 3 minus 3x squared. I'm just going to quickly go ahead and solve that. X gives me plus or minus 1. So I'm going to add 3x squared on both sides, divide by 3, square root both sides, plus or minus 1. Now, of course, there's two values of 1. What I'm going to do is I'm going to actually draw a quick table where I've got -1 here as my x value. I've got -1. I've got 1, and then this one will be my dy dx. And I'm just going to draw a quick table like this. You'll note I've included spaces for values in between and on the edges as well. It doesn't actually matter what those numbers are as long as they are from the left and the right, because it doesn't matter if I've got bless you. It doesn't matter if I've got 2 here or I've got 200, because I know that the gradient is either going to be positive or negative. It's not going to be changing from positive to negative at any stage, because the stationary point is at x equals to 1. Now, I'm not going to choose substituting x equals to 200 because that will be a waste of time. So instead, I'm going to pick a number that is nice and easy to fill in. Same thing for here. I'm going to obviously put in 0. It's a nice, easy number. And here, I'm going to put in -2 as well. So hopefully, they should be in chronological order. They all fit nicely. Remember, I'm substituting back into the gradient function, because remember, I'm trying to find the nature of the stationary point. That is a key term you hear very often throughout the year and the exam. The nature of the stationary point. Is it a maximum, local minimum, etc.? Very easy to fill in. I know that -1 is going to equal to 0 if I substitute it into the derivative function. So I can signify that just drawing a line, a flat line. If you want to write 0, it's fine. Assessors aren't going to mark you on this explicitly in terms of notation, because you're just using some working steps to get to your point. Now, of course, the same thing applies for 1 as well. I'm going to substitute one of these values in. 0 is easiest for me. Again, remember, I'm substituting into the gradient function. So substituting 0 for x here is going to end up being 3. So it's a positive value because it's 3 minus 0. Therefore, it's going to look like that. If I substituted 2, and I'm going to put the steps in here. So let's say at x equals to 2, I have 3 minus 3 times 2 squared. 3 minus 12 gives me, and it doesn't matter how negative, I know it's a negative. I don't need to bother. I can just draw a line straight down. And of course, same thing if I put in 3 minus 3 bracket -2 squared. That gives me 3 minus 12. Again, it's a negative value, so therefore it's going to go down like that. Just based off this, and I'm using a generally more simple example, based off this, we can tell that at our first stationary point where x equals to -1, it's going to be a local minimum. Our function goes down to that point. And the same thing, or its opposite thing, sorry, at x equals to 1, it's going to be a local maximum. Now it says find the stationary point, so what I'm going to do is I'm going to substitute x equals to -1 back into the original equation. So I get y equals to 4 plus 3 bracket -1 minus x, oops, not minus x, minus -1 cubed, which would equal to 4 minus 3, that becomes plus 1, which gives me an answer of 2. I'm going to do a similar idea for this one over here, which is x equals to 1, y equals to 4 plus 3 bracket 1 minus 1 cubed. Am I going too quickly at all? Which equals to y, that's 4 plus 3 is 7, 7 minus 1, therefore it's 6. So my coordinates are -1 and 2, 1 and 6. Again, you don't want to make the mistake of saying x equals to -1 and 1, y equals to 2 and 6. You must have coordinates. And then, of course, we need to label them as what the stationary point's nature is. X equals -1 is a local min, and this one, of course, is a local max. If you end up with a function where you have something that looks like a stationary point, and then it's a positive gradient on each side, so something like this, that is a point of inflection. Okay, you're going to have a positive gradient flatten to a 0, and then another positive gradient, that is a point of inflection. Another way you might do this kind of question without having to bother going through these steps is just look at the graph and think, can I visualize what it looks like without doing all these steps? I know that -x cubed plus 3x plus 4 is a negative cubic. I know negative cubics, instead of rising up with the first bit of the function, goes down and then back up and goes down again. Right? That follows the general trend, and so you can identify based on whether it's on the left-hand side or on the right-hand side, it's going to have a local max or local min. Any questions? No? Okay, I'm going to do a very quick recap just in case you weren't here when I went through that lesson. Generally speaking, if it's a power 1, 2, 3, and 4, of course, if it's a positive function, then our function rises first, our function decreases first, rises first, and you get the idea. Okay. Now, of course, we're assuming that these are not in our quote-unquote turning point or point inflection forms. If that's the case, then it takes on a unique function, a unique graph. Cubic functions become a point inflection, and of course, powers of 4 or powers of even numbers become a turning point function as well. That's it. Any questions? Okay.